Part E of this example asks to evaluate a prime of 12. So what it's asking is, at what rate is the area under the graph of f of t changing at t equals 12? So without further ado, let's take a look at the graph. Okay, so here's the graph of f of t, this line, and what a of x represents, as we've gone over before, is a function which tells you what the area between the graph of f of t and the t-axis is. Okay, so a of x is the area function. What a prime of 12 is asking for this particular part of the example is at what rate is the area under the graph of this function changing at t equals 12, at that exact t value at t equals 12. At what rate is this area changing? Well, we can see it's increasing simply because it's above the t-axis, so all this area will be considered positive, and it will increase the area. But what is that rate? And as a consequence of the fundamental theorem part 2, we said before, when we explained that theorem, it's actually equal to the function value. I'm going to give you two reasons why that is. First, recall that f of t is actually the derivative of the area function. So f of t is actually the same thing as a prime of x. Okay? So what that means is if you look at the y value at 12, it's 1. That tells you automatically that the rate in which the area is increasing between the graph of f of t and t is 1 unit squared for every unit x at that particular point in time. So here's the first way I like to explain it. Suppose the graph just remained at the y value being 1 or the f of t value being 1, and it just stayed that way forever. Well, you can see that for one unit change in t here, or x, we're going to increase the area by 1. Okay, this new area added would be a 1 by 1 block. Okay, I know it's not a perfect square, but you can see the y value is 1 and the change in x is 1. So there's one way of confirming it, is that if it were to stay at that y value, which actually gives you the derivative of a of x, it would increase by 1 square unit for every increase in x. Now we're talking about a particular t value right at t equals 12. So it's kind of like the speed of a car. You know, how fast is the car going at time t equals 12? It's going 1, mile per hour or 1 meter per second, whatever. The other way I like to explain it is by using Riemann sums. So if we were to try to find the area under this curve using Riemann sums, we would see that at this particular t value, the height of that rectangle is 1. Okay, that's the y value. And so the only thing that's going to influence the rate at which this area changes is the height of that rectangle, okay? The width, if we use the same rectangles, the width isn't going to change, right? It's always going to be the same. And even if we make infinitely many widths, that's definitely not going to have an impact on the area. The only thing that's going to have an impact is the height of that rectangle, and in this case it's 1, and therefore the rate in which the area is changing at t equals 12 of this graph f of t is 1 unit squared. Okay, so due to the fundamental theorem, the area formula that we found in a previous example is irrelevant. We don't need that piecewise formula. We know that because of the fundamental theorem part 2, the rate in which this area is changing at 12 is just equal to the y value, or the f of t value at t equals 12. And so that's because a prime of x is equal to f of x. In other words, the function value f of x gives you the rate at which the area is changing, and therefore a prime of 12 is equal to f of 12, what we just determined looking at the graph. F of 12 is equal to 1. So looking at the graph f of 12 equals 1, this means that the area under the graph of f of t at x equals 12 is changing. Okay, it's the area isn't 1, but it's changing at a rate of 1 unit squared for every 1 unit x at that particular point in time. That's it for this question dealing with area function, and it actually ended up being one of the easier questions we've answered in this lesson. If you have any other questions about this, let me know.